Welcome back, student tutorials. In this video, we're going to be looking at the process you should follow when you're decomposing a program or a problem, and then we're going to be looking at some things you should think about when you're doing this as well. So, to get this point across, I've chosen an example which I think is quite relevant to physics, actually. And what it is it's a program that I developed a while back now. So what it does is it simulates planetary orbits in 3D. So you can create planets, you can see how their gravity affects them, you can move around, you can play with them, see what happens. But this is a pretty massive project, and it took me quite a long time. It's got lots of moving bits to it, and it's more than just simulating gravity. So for the purpose of this video, we're going to simplify it slightly, and we're going to take out some bits, but we're going to keep the same idea of the project. We're also not really going to be looking at any actual code or advanced programming concepts. We're simply going to be thinking about how we would break this problem down for you to do it. Now, when I did this project, I did it in a program called Unity. Unity is a game engine, and a game engine is essentially a program that lets you make games. So I'm sure if you've ever played many games, you probably will have played a game made in Unity. But what Unity gives me is a 3D space that I can work in. So it means that I didn't have to program it myself. I can, it gives me tools that lets me create objects and move them about and move about within that world as well, so that all I have to do is tell the program how I want to use those tools, as opposed to actually programming the tools myself. It saves a lot of time, and realistically, there's no point programming something that has already been programmed, especially for something like this. So, the first thing you need to think about when you're trying to solve a problem or do a project is, what do we actually need in our project? Well, we need the fact that we need planets, we need to simulate gravity, we need them to move about, and we need to have them representative as, at least as spheres, but there's lots of other stuff that's in real life that we don't necessarily need to get the idea across. Well, obviously, real planets are not totally uniform. The Earth has bits where the gravity is stronger than others, but that's a very complex program, so we're going to get rid of that. You might have relativistic effects. Maybe if one of the planets was really massive and it was accelerating around, you might get gravitational waves or things like that. And also, obviously, the Earth rotates. Most planets rotate. So we're not going to simulate that either, because, again, that's a pretty complex program, and it doesn't really take away from the idea we're going to cross. So what are we going to do? Well, we're going to model the planets as uniform spheres with no detail or color, so they're just going to be boring grey spheres. And we're also not going to include any of the effects that I just listed above. Now, this process of removing this detail is called abstraction. And yeah, as I said, it's the first thing you always need to do in doing a project. It's just getting rid of detail, which is going to make your project harder than it needs to be, and it leaves you with a problem that is generally much easier to solve. Okay, so once you've removed at least the base details that you don't want to include in your project, what you need to do is you need to start breaking your problem down into sub-problems. So smaller problems that make up the bigger problem. So our big problem is making a simulation program that simulates planets in 3D. But to start with, we can break that down into two sub-problems. We've got the bit of the program that will do the simulation, so simulating gravity, moving the planets about, and then we've got the bit of the program that will control the camera. What do I mean by that? Well, when if you've ever played a game before, 3D game, you will be moving about, and what you're actually doing there is you're controlling a camera. You're controlling where the camera looks and where it moves. So we need the same in this. We need to be able to move around our 3D world, and we need code that does that. For the purpose of this video, we're not going to be looking at the camera movement side of things. It's not entirely relevant to physics, so I thought I'd leave it out for now. Okay, so we're looking at the simulation bit of the program. Let's break that down even further. Well, there's obviously going to be gravitational force acting on those planets from each other, so we need a bit of the program that calculates that force. And from that force, the planets are also going to be moving about, so we've got to have a bit of the program that moves the planets about. So already we've split our big problem into smaller problems that are already a lot easier to solve than the big problem, aren't they? Okay, so let's look at the force bit first. How are we going to calculate the force on planets? Well, all we're going to use is Newton's law of gravitation. And Newton's law of gravitation says that the force acting on one object is equal to the sum of the forces from the sum of the force of gravitation from all the other objects surrounding it. So I've got that represented in a mathematical way here. I represents the planet that the forces are acting on, and J represents all the other planets. So essentially what this equation does is it says, okay, let's say I had 3 planets. Let's start with planet 1. Now, let's move through the other planets, not including planet 1. What is the force acting on planet 1 from planet 2? Okay, work that out. Then what is the force acting on planet 1 from planet 3? Work that out. And you add all of those forces together. And the sum of those forces will give you the overall force that is acting on planet 1. You then do the same for planet 2, and you do the same for planet 3, and you can do this with as many planets as you like, really. Okay, so we've got the equation we're going to use in our program. Now, equation, to work out the force, it needs the mass of the planets, and it needs the distance between the planets. But for now, let's ignore things like the mass and the size of the planet. So we're just going to consider them as point objects, like you would have done at school. So they're just, an infinitely small point where the gravitation is seemingly acting entirely from. And for now, we're just going to say that the mass of every planet is exactly the same. So there's no variation in mass for now. It's all just the same. We first need to obviously create those planets. That's another thing we're going to need to do. We're going to so that we can actually simulate the effects on them. Luckily for us, Unity is a tool that can do that. Great, you can create objects in Unity. Okay, so how would we actually calculate that force in code? Well, that equation really, moving through those planets, is actually a form of iteration like we discussed in the last video. We're applying the same code essentially to just different objects, different planets. So we can just iterate through them one at a time and do that, which is great. And because mass and sizes are the same, the only thing we need to get is the position of the planets, so we can work out the distance between them. Okay, so we've got even more tasks now. We've broken them down. So we've got to create the planets, obviously. So there's gravity between them. Then we've got to iterate through those planets. We've got to get their position, each of their positions, so we can work out the distance between them. And then we've got to use Newton's law of gravitation. Okay, so the problem with working out the force, I think, has been satisfactorily broken down into smaller problems. You'll see if you look back at this slide that if you look at each of those problems individually, they're not that difficult really to solve. Each of those problems could be solved in a few lines of code, and that's exactly what we want here. We want to make our problem easy to solve. So the next thing is, we've got the force, now we need to actually move those planets. Well, luckily for us, there's more equations we can use. We can just use the equation of motion, SUVAT. We have a force from Newton's law of gravitation. We have positions, so we can work out distance, and the masses are all the same. So if we have a force and we have a mass, we can get acceleration. And then we can just use that acceleration and a time, which will be we can get from Unity, to work out a displacement and velocity. Okay, so we can use this. Once we have the displacement, Unity makes it very easy to move those planets. Again, you need as many tools, so we can just give Unity that displacement and it will move those planets for us. Now, obviously, after we've done this whole operation, the planets will have likely only moved a very small amount. But what we're doing is we're doing this operation every single frame that is shown on the monitor. What do I mean by this? Well, anytime you play a game or whatever, what's really happening is your screen is just showing you lots of pictures shown in really quick succession. So what we can do here is we can run this process every single frame, and we can take the time between each of those frames, so the time taken to get from one frame to the next, and we can use that time in our equations of motion, because that time will be the difference in time that we need. That's the time the planets will have been moving for. Well, I guess they're not on the screen. We can use that data. Okay, so this is our move planets bit. So to do that, we've got to calculate acceleration. We've got to work out the displacement from the acceleration and the time and the velocity that we will have also worked out. We then got to transform the planet. By transforming the planet, I just mean move the planet. That's another word for it. And then we've got to work out and save the velocity for the next time. So we've got to work out how fast the planet was moving so that next time we're using S as ut plus a half at squared, we have a u. We have a u that we can use, initial velocity. So putting all this together, we get this. This is our simulation bit broken down into lots of subproblems. So some of these you might understand. This is actually the diagram I used in my documentation when I was making the project. So you've got to calculate the force, you've got to get their position, save position, same thing. You've got to iterate through each of those planets. The inherit bit you can ignore for now, that's not particularly relevant. You calculate the delta in distance and time, so you calculate the change in distance and time. And then you use Newton's law, calculate the acceleration, then from that you can calculate displacement, blah, blah, blah. We've gone through that. Great. The process you've just gone through is called decomposition. This is the process of breaking a pretty big problem down into lots of smaller subproblems. So if you noticed before, the problem seemed really difficult and you might not even know where to start here. But now we've broken it down into subproblems, you can tackle each of these problems individually and then just put them all together and you would have solved the problem. Okay, now what else does decomposition help us as well? I'll explain what a function is first. A function is a block of code that performs specific tasks. That can be called and can be reused multiple times. So if you have a few lines of code, you can give it a name and essentially run that again and again and again. What decomposition does is it generally shows you which of your code should be in one function or script. And that's really good practice in general. Having your code mostly within functions and separate scripts is called modulation, and modulation is very good. It makes your code more readable because you've generally got pretty good names for each of the sections of code, and most importantly, it makes it reusable. So maybe you do this project and you've got all these functions and you've got all these scripts, and then you do another project, and it just so happens that some of the functions and scripts that you made in this project you can use in your new project. And because you've got them separate, they don't necessarily rely on the rest of your old code to work, and so you can just reuse them and save time. So now we've got lots of problems. We need to think about what kind of information do we need in each of our functions and scripts. Well, for this, we're going to need variables. A variable is essentially a name given to a slot in your computer memory. So imagine it like an address of a house, really. And it stores data. So this data can be anything from a number to a picture. Each variable, normally, each variable has what is called a data type, which, as given by the name, is the type of data which you're going to store in a variable. This could be an integer. It could be a float, which is just a number with a decimal point. It could be a string, which is a word or collection of letters. So it could be anything, including letters. Or even numbers, if you specify numbers being a string. Or it could be a bool, which is you saying true or false, so conditional statements. Now, there's lots more data types than these, but these are the most important ones and generally the foundational ones you need to think about. There's also two types of variable, so not data type, there's two types of variable. There's local variables and there's global variables. Global variables can be accessed anywhere in your script. So let's say you have a script, one script with a bunch of code, and in that script you have a bunch of functions that do completely different things. If you have a global variable, you can access that variable, you can use that variable anywhere at all in that script. So in any of the functions, you can say, I want to use that variable. A local variable, however, is defined within a function. So let's say you have a function where it's just a specific thing. You define a local variable. Generally, that local variable can only be accessed within that function. So if I was to try and in a different function say, I want to use that variable, the code would go, I don't know what you're talking about, unless obviously you define otherwise. So as an example, I've put a list here of all the variables that I used in the calculation part of my program. So you've got things like distance. So you'll notice that distance, you've got x, y, and z. We're in 3D, so we've got 3 different distances. We've got velocity, we've got the mass of the planet, we've got acceleration, we've got displacement, and then we've got total force and things like that. There's other variables that you don't need to worry about. not really relevant to this video, but I thought I'd just show you this here as an example of the kind of variables you might need. I'll leave it to you to think about whether these variables should be local or global, and whether you think you could keep them in a function, or whether it would be easier to have them in just all global like they are here. I've also then put some of the code, which I again had on my project. So on the left, you'll see the script that primarily deals with all of the movement. So you'll see that at the top, it's in this void update function. What that means is that whatever's in that void update function will run every frame, and we need that. So this will run every frame that is generated by Unity. And you'll see I'm working out velocities, I'm working out accelerations, I'm working out displacement, and then in the middle of that script, I'm running the script up here. I'm running this force calc function as I made, which is the script that it's the force acting on the planets. And like I discussed, it iterates through the planets, it sums their forces. So yeah, again, don't concern yourself with any of the actual syntax of this code. That's not particularly important. What's important is that realistically, each of those bits that we've broken that problem down into can be done in just a few lines of code rather than a massive script. So why do all this before you program? Maybe I haven't convinced you yet. Well, when you're programming, you should always be following a process of problem solving rather than just trying to jump at the problem and hoping for the best. Trust me, every programmer ever would have probably done this at some point, where you just jump at a problem and you just try to solve it all at once, and it's just genuinely too big for you to think about sometimes. You cannot get your head around it unless you follow this process. If you're tasked with learning a new language as well, this makes it much easier. The syntax of the language should be the only thing you have to learn. Once you've broken down your problem into subproblems like here, you don't have to think about that much anymore. The only thing you have to concern about is, how am I going to program that? What tools do I have in the language, and how should I write that for it to actually work? Now, if you have the logic and method of thinking, the syntax is generally very easy to pick up, and in most languages, it is kind of the same. Now, I haven't touched anywhere near the entire scope of this project. There's a lot more to this, but the process you need to follow is exactly the same. You can break down any bit of this problem exactly how we have done here. There's just not enough time in this video for me to cover everything. Always make sure when you're programming to follow good coding practice. It might seem monotonous at first, but trust me, when you get to bigger projects, it will help a lot. Anyway, that's it for this video and for the mini-series as well. I hope you found it helpful, and I hope that you got something out of it. Thanks for watching.